klomp classes in 'n conglomerate. En dan kan jy sê, okay, en elkeen is non-empty, so ek pick 'n member uit op. En dan kan jy nog 'n hoër axiom as dit vir die conglomerates doen, wat jy nou dink hulle noem dit 'n super conglomerate. So dit is 'n collection wat groot is vir 'n conglomerate. I mean, jy kan transfinite reduction many times aangaan soos jy wil en hierdie hierarchy van set theories bou. En elke keer is die een soos groter as die ander.
Maar dit na 'n punt.
Nee, dit stop nooit nie.
Ja, maar soos na 'n punt is dit nie net erg sinvol om te...
Wel, dis nie, ek dink nie dit is meer sinvol om te dink aan die size nie.
Ja.
As jy tot my conglomerates kan gaan sien. Vir nou. Tot op hede het ons nog nie in wiskunde nodig gehad om met iets groter as 'n conglomerate te werk nie, as dit die vraag vir jou. Nie waarvan ek weet, dit is dalk moontlik dat iemand dalk al het, maar sover ek weet was dit nog nie nodig om na iets groter te gaan nie. Maar dit is 'n interessante vraag nou, byvoorbeeld, as ek net vir jou sê, G is 'n groep. 'n groep is 'n klas. Dis 'n proper klas, of al die groups is 'n proper klas. So
Ek na die axiom of choice kyk en probeer uitfigure dat hy nie op my sneak af nie, want elke nou en dan jy moet so self in 'n probleem in.
Jy gaan baie keer, jy sal nou sê jy die meer van oplet daarna. Maar byvoorbeeld, okay, so standard topology proof. Gewoonlik kom ons gebruik sommer die rationals en die real numbers en ons doen 'n ou reële analise bewys. Ek weet nie of jy onthou wat dit beteken vir 'n subset van R om dens te wees.
Is dit nie
elke bol by enige punt met enige arbitrary radius intersect.
Ja.
Of elke open set van R of Rn in general contain ten minste een punt van die set. En noem ons dat set dens. So byvoorbeeld key is ons nou dens in R. Right. So ons sê key is dens in R, maar met ander woorde jy moet net bewys dat die closure actually R is. Dis 'n ander is 'n equivalent definition. Dit bewys gebruik die axiom of choice. Countable choice, maar still choice. In fact, jy kan ook bewys dat jy kan nie die real line gaan skryf as 'n uncountable union van open intervals. En dit het iets hiermee te doen, maar nie raak wat nie. Maar gaan try dit. Disjoint intervals, sorry ek moet dit wys.
Okay, ja, ek wou net sê dis.
Ja, obviously, ja, jy kan net minus AA vat. Maar okay, so in ander woorde, as R geskryf word as die union van, kom ons noem dit nou maar A alpha, B alpha intervals, waar alpha in een of ander index set is, en vir elke alpha en beta en I is, wel, kom ons sê as die twee nie gelyk is nie, is A alpha alpha is intersection met A beta, B beta, as dit 'n empty is, met ander woorde elke is pairwise disjoint, al die intervals. Dit impliseer I is countable. Ons nou kom by cardinality anyway. In ander woorde, I moet finite wees of at most countable.
Dis 'n countable basis.
Dit het iets daarmee te doen, ja. Al dit het baie te doen met die feit dat R 'n metric space is.
Maar ek wil daar nog van waai.
Ja, maar ja. Bly dit hoor. So ja, dis basically, dit is ook iets wat volg. Dit het iets te doen met die density, maar dit het baie meer eintlik te doen met die feit dat R metric space is. En hy het 'n countable basis. Yes. Wat jy kan al die balls met rational centers vat, while Rn generally. Rational centers, die centers van al die coordinates moet rational wees en al die radius is moet rational.
Dis nou waar jy kies die rational center van elke bol.
Ja.
Dis nou waar
elke bol moet rational wees, elke endpoints, met ander woorde as dit in Rn is, elke koördinaat moet rational wees en die radius moet ook rational wees En al daai balls gee vir jou 'n countable base.
En dit
En natuurlik dit is 'n metric space.
Dis daai keuse van die center van daai balls en die radius van daai balls. Dis wat
Wel, dis
die maximum choice doen.
dit is kind of wel nie so baie nie. Dit kom meer in kyk jy kan 'n countable base kry, maar die ding is daar's 'n theorem vir metric spaces. Ek weet nie of jy dit onthou nie, maar daar's 'n theorem vir metric spaces, jy sal dit nou nie onthou nie. Maar daar's 'n theorem vir metric spaces wat sê die metric space het 'n countable basis as en slegs as hy separable is, wat beteken daar is 'n dense countable subset. En as en slegs as hy Lindelof is. Wat beteken dit is amper soos compactness, maar die enigste verskil is every open cover has a countable subcover. So daai drie goed saam en jy kan gaan kyk na daai bewys. Axiom of choice speel 'n rol.
Ek sê
Die probleem is kom ek gee vir julle 'n idee. So as jy weet as jy wil bewys key is dense en jy gebruik nou hierdie countable base dan of kom ons sê liewer so, kom ons bewys liewer R is separable. So ek vat 'n countable base, meaning ek gaan kyk na alle key minus epsilon, key plus epsilon, waar key en epsilon beide rasioneel is. So ek kyk na al daai intervalle. Dis 'n countable base vir R. Okay? En nou al wat jy van hier af kan doen, is jy kan nou sê, okay, kry vir my 'n countable dense subset. Vir energie. Wel, jy het 'n countable collection van intervalle en jy kies net 'n punt uit elke interval. Axiom of countable choice. So om 'n countable dense subset te construct, gebruik jy die axiom of countable choice vir en vir R in similar argument. So axiom of choice is jy al baie gebruik, jy het net nie geweet nie. Die analytic van analytic completion van 'n complex valued function. Axiom of choice.
Dis so sneaky want jy toe nog nooit raak gehad. Jy moet opgelet om raak te sien.
Maar nee, jy gaan nou. Glo my, jy gaan nou. Ja, maar jy gaan begin kyk vir dit. Wat 'n goeie ding is dink ek. Wel as jy nog nie daarna begin kyk het nie, jy moet begin dink daaraan om daarna te kyk as jy dit nog nie begin doen nie.
Dit is hierdie wat die infinities begin gebruik en jy besef nie dat jy actually gebruik.
Toe maar ons gaan well, by the way, wil julle nou Woensdag klas hê of eers vir 2 weke?
As Woensdag ek het net 3 of 4 uur het ek 'n vergadering in die middag. So enige ander tyd die dag is reg.
Okay, wel ek is Woensdag pretty much ek het 'n klas van 9 tot 10. So enigiets van 11 uur af is ek ook basically.
11 uur dag is net jou.
Ek weet nie hoe lyk jou dag nie. 11 tot 1. Okay, dan moet ons net ek dink ons gaan dan dalk met 1 en 9 toe gaan.
Die topology class se boek. Dit was al.
Was mos in hierdie venue. So ons kan net weer hiernatoe kom 11 tot 1 Woensdag. Dit is perfek. Okay. Ek doen dan doen ons dit. En dan sal ons bietjie begin praat oor cardinal numbers ook. And especially as baie mense sal vir jou sê set theory is really the mathematics of the infinite. So at some stage moet ons seker daaroor begin praat. I mean, what is infinity? Maybe we should change it to infinity theory. But anyway, right, so to get started. Okay, so, let's see, right, okay, so, first off, I'm going to start with the definition by saying, if I have two sets, x and y, then I will write it like this, okay, and I will say, so this is just my notation, but it says x is equipotent to y, x and y are both sets here, keep in mind, if there is a one-to-one correspondence between x and y. Okay, what there's a one-to-one correspondence between two sets, there's a bijection between. Okay, so of course x is equipotent to y is also the same as y being equipotent to x. Okay, so in some sense you can view this as a relaxation of the isomorphism theorems. Or not isomorphism theorems, just set isomorphism, sorry. Or just, you can view these as set isomorphisms, that's the idea here. Okay, so basically we can think about sets as having the same size, because now for finite sets, of course, it's clear, because our idea with introducing the natural numbers in the first place was to say, okay, but now we can say, okay, we say a set is finite exactly when it's equipotent to some natural number n. Okay, so using this, I will say that x is finite if there exists some natural number for which x is equipotent to n. And of course, such n will be unique. Okay? And we say that x is infinite when?
When there doesn't exist.
When it's not finite. Okay, so exactly, when for all natural numbers, x is not equipotent to n. Okay. Right, now of course we already have an example of a set that is not finite, which is? Yes. So omega is not finite, it's infinite. And in particular, when a set, if x is equipotent to omega, then we call x denumerable. Okay, or another name for it is countably infinite. Please note this is not the same as countable. Countable means denumerable or finite. Okay, so these are strictly sets like, for example, we will also talk about this today, like the rational numbers is denumerable. Every natural number is of course not denumerable because it's finite. So a denumerable set is by definition one that's equipotent to omega. Okay, it's a countably infinite set. So it is countable, but it's not finite. Okay, right. So this is what we call here now. We do kind of want to start to define an ordering on sets, so to speak, in terms of size. Okay, now, unfortunately, there's no way that we can have an ordering that will be anti-symmetric. Okay, in other words, if A is smaller or equals to B, and B is smaller or equals to A, then B is equal to A. Because I can take two singleton sets, and now if there's a bijection between them, cool, they're the same size, but of course the two sets are different if you have two different singletons. So we can't really have an anti-symmetric order. However, if we think about finite sets, and now we think about just the natural numbers here, because we can, in some sense, via our bijection, we can represent every finite set with a natural number. Okay? Because if it's finite, then there is such a bijection, and then guess what? If you have this bijection, let's say the bijection goes from n to my set x, then I can also well order x without using the axiom of choice. Why? Because I can say x, actually let's choose the bijection to go in the other direction. X is smaller or equals to y in x, if and only if f of x is smaller or equals to f of y as natural numbers. Boom, well ordered. Every natural number is well ordered. Every non-empty subset of any natural number has a meaning. So we can well order every finite set. No axiom of choice necessary. Well, we can anyway well order any finite set, you might say, without even doing this, because you take two elements at a time. You start with the first element you like and you call it the meaning number, and then you just construct one bigger, and you can do that in finitely many steps, provided that the set is finite. But just think about the idea because we will later on extend it. So what we really want is we want to build like a theory where we have infinite numbers as well. And that's when we'll get to cardinal numbers. I don't think we'll get to that today, but definitely Wednesday. Okay. But so the idea is we kind of want to have, if I have any pre-order, because this will be a pre-order, okay, why do I say it's a pre-order? Why is it reflexive? In other words, not this particular ordering, but so what I'm going to do is, I will say that I have a set X is smaller, and I denote it like that. It looks like a little tilde smaller or equals to. So it does kind of look like that rather. Okay, but anyway, so I will say, think about is the size of X is smaller or equal to the size of Y if there is a one-to-one function f from X to Y. Surely, for finite sets, that works. Right, so we kind of want to extend the idea to infinite ones. Because if I can find a one-to-one function from a set with m elements to another set, then that other set must contain at least m elements, otherwise it can't be one-to-one. So the idea is to use this, okay, and so we say that x, by the way, if x and y are equipotent, then we sometimes also say x and y has the same power. Okay, the same power is another term for equipotent. Okay, so we would say that x is of lesser or equal power than y if there's a one-to-one function, and then we will also say x has strictly less power than y if x has less than or equal power, less than or equal to the power of y, and x and y are not equipotent. In other words, there's no bijection between x and y, but there is an injection from x to y. Okay, so same power, equipotent, less than or equal to, could be bijection, but generally just injection, and strictly less than, just injection with no bijection. Okay, from x to y. Okay, so this kind of gives you the idea of going larger in sets. Now, for this is a pre-order. If I use the smaller or equals to, okay, so power less than or equal to, why is it a pre-order? Okay, well, what is a pre-order? Okay, by the way, so it's of course here, it's a relation on the class of all sets. Okay, so is it reflexive? Is x equipotent to itself? Yes, you can take the identity function. Is it transitive? If x is lesser or equal power to y and y is lesser power than z, then of course you can just compose the two injections and you can see it's transitive. Now, what you usually can do if you have any pre-order, so I'll just give you the idea, if x is a set and you have a pre-order, call it smaller or equals to, then I can define an equivalence relation, namely, I define x and y to be equivalent if and only if x is smaller or equals to y and y is smaller or equals to x. Okay? And then I look at the equivalence classes and I define an ordering on the equivalence classes by saying this equivalence class, and I will just use a square ordering here. I'll say that is smaller or equals to that if and only if x is smaller or equals to y in the original order. And I can show that this is a partial order on the equivalence classes. Okay, so the idea here, if we go back to sets, would be, okay, we have a pre-order on the class of all sets, and now we can say, okay, cool, we define two sets to be equivalent if the one is smaller or equal to the other one and the other way around. Okay, we haven't done that yet. Okay, and then we want to say, okay, cool, now look at the equivalence classes. And now you want to say, okay, cool, then I can pick an element out of every equivalence class. Am I allowed to do that? No, not. Why not? Because we have an equivalence class of classes, not of sets, and our axiom of choice for sets does not allow us to pick an arbitrary element of a class, only a set. So if you have an axiom of choice for classes, sure, you can use this idea to then actually just construct, you just pick a member out of every single one, and it would be nice if that set has nice properties too. Like for instance, maybe it would be nice if it's well ordered. I mean, if we are already invoking the axiom of choice for classes, you might as well say, well, the set is well ordered. Well, it turns out, this will kind of be the idea, but we will not use the axiom of choice. We will have another axiom. But basically, if you want to use the axiom of choice for classes, you don't need to have another axiom. Hence, axiom of choice is the best. If you ask me, especially if you work with the one with conglomerates, I use it all the time. Well, not all the time. I prefer not to use it if it's not necessary. But sometimes you just got to say, look, we want to do interesting stuff. But truth be told is, I mean, if you want to use the axiom of choice for classes, then you can actually do this, and then we will call these representatives the cardinal numbers, and turns out there's a way in which we can make them all well ordered, in which one cardinal number is smaller than another one exactly when it's a subset, exactly like the natural numbers work. So the natural numbers will be our finite cardinal numbers, but we also want to do ones for infinite. Okay, but we'll get to that a bit later. Right. So that is just, okay, so that's denumerable, of course, and countable, and you know it's finite order numerable, and then I just want to make, so you all know why the rationals is countable. You've probably seen the proof in real analysis. The idea is usually you go and say, okay, I start with 1 over 1, and then I have 1 over 2, 1 over 3, 1 over 4, etc. Here you have 2 over 1, 3 over 1, and then you continue in this fashion, and then you usually just do this, and then eventually you can list them while also not repeating the same fractions. Okay, but they anyway give you a nice way if you don't want to draw the picture. They just tell you you group all the positive rational numbers. We only look at the positives because we can easily find a bijection between the positive ones and all the natural numbers. It's not hard. Well, if you first want to exclude 0, then if you have an enumeration or list by saying it's A1, A2 up to, well, of course, infinitely many, well, you have a list. If you want to include the negatives, you just make a new list, A1, negative A1, A2, negative A2, and you can continue in that manner. And then, of course, you just have to include 0, but we'll also prove now, by the way, if you have any countable set, by removing any finite or adding any finite set, it remains countable. Okay. And a similar thing will later on be true for infinite sets. Okay. If you remove any smaller cardinality or add any smaller cardinality, it's not going to change the size of the set. Okay. But of course, that's just true for infinite ones. For finite ones, it's of course very different. So infinite cardinal numbers, we will be able to add and multiply them to. Okay. Right. Okay, so, and then also with the real numbers, you've also probably also seen that they are uncountable. It's called Cantor's diagonal argument, but the idea is just, you can find a bijection between the open interval 0, 1 and r by just using some translation of tan, or arctan if you like, or depending on from which direction you go. But so, the open interval is actually homeomorphic to r, but there's a bijection, and so by adding 2 points, it's not going to change the size, but usually they just show that all the real numbers between 0 and 1, so if you want to write them like this, and here we of course, even if the rest of the digits are 0, we continue enumerating it. So here we have 2, 1, and then R, 2, 2, etc. So you have R31, R32, and generally 0, Rn1, Rn2, Rn, well let's rather make that K. You get the idea, it continues like this. So if there is an enumeration of the real numbers, then all you do is you pick you must be a little bit careful with your choice. But so what I would do is you would say if we're going to define a real number, if R, so we're going to look at RII, so if this was a matrix, so to speak, forget about the zeros, just the diagonal of this infinite matrix. If RII is equals to 9, we define SI to be 2, and if RII is not 9, we just define S of I to be RII plus 1. And then our real number, S, we define the 0.S1, S2, or if you want to be more exact, no, from 1. It will be the limit, or it's just the sum of the series. Like that. Okay. Also, the real numbers can also be constructed. So what we can do is I'll later on also prove that the product of two countable sets is countable, the union of countable sets is countable. We get to all of that. But the idea here is that you can view every real number as an equivalence class of Cauchy sequences, where you say two Cauchy sequences are equivalent provided that they have the same limit. Okay, or to be more exact, because we don't know what real numbers are, if you have two sequences, let's say x and y, and you want the limit of xn minus yn to be equals to 0. Okay, so there, that's when two Cauchy sequences. So if x and y are Cauchy sequences, then we say that they are equivalent provided that this limit is 0. That gives you an equivalence relation between all Cauchy sequences, and the equivalence classes is just actually the real numbers. Okay. But so I'm not going to talk about how exactly you can construct them, but basically you can use the natural numbers, and then you can think about the natural numbers as pairs. So if you think about a subset of omega cross omega, then you can view mn, now as I remember there, as just the integer m minus n. And you define an addition and a multiplication in the ways that would make the normal axioms we want to be true work, and then you get your integers from there. So the integers, you also then get an equivalence class. You say that this is equivalent to PQ, provided that m, you want m minus n to be equals to p minus q, so m plus q must be equals to p plus n. That's how you define the relation there. You get the equivalence classes. They are algebraically, as a ring, isomorphic to the integers. And then you use the integers and you use the original field of quotients construction for any integral domain to get to the rational numbers. And then there are two ways you can go. Both involves a bit of field theory, or Galois theory. But basically you can look at one way from getting from reals to complex is you look at, first you can start with the rationals, so from rational to complex there are two ways. The one is by first using all these Cauchy sequences to get to the reals, and then you use Kroneker's theorem, which says that if you have a field, like the real numbers is a field, and you look at all the roots over all the polynomials with the coefficients in them, then you find the algebraic closure. By the way, to get the algebraic closure of a field, that always also involves the axiom of choice. But it turns out the complex numbers is algebraically closed, so we're kind of lucky that we don't actually 100% need it. But you can still, to prove that it exists in the realm other than, okay, well, here we have this number system and it satisfies all the things. You do need the axiom of choice to know that it generally exists. So for Kroneker's theorem, it does depend on the choice because it depends on the existence of an algebraic closure. But as long as the algebraic closure exists for a particular field, we don't have to worry, and C is algebraically closed, so we don't have to worry about the real numbers. So then you can just construct the root of x squared plus 1 over the real numbers to get to the complex numbers, They will also be uncountable, just like the reals, and the rationals will be countable. And the other way is you go from the rational numbers and you first look at all the roots of all polynomials with rational coefficients, and then you get something which is a subfield of the complex numbers, a proper subfield, which is usually just called the algebraic closure sometimes in textbooks. But basically it contains all the algebraic numbers, which are all roots of polynomials with rational coefficients. These of course include all your, if you start with rational numbers and you use operations like addition, multiplication, taking nth roots and stuff like that, you get all the algebraic ones. Okay. You do not get all the numbers because of course, by the way, the probability of choosing a number and its algebraic is 0 because they're still countable. And so the algebraic numbers is a very small part. Almost all complex numbers, and by saying almost all I mean literally, the probability is 1, will be transcendental. So stuff like E, like the golden ratio, no, not the golden ratio, sorry, but P as well. And there's a few others but most of them are. So basically, you think about irrational numbers where you can't really see any pattern and nobody knows how these numbers continue. Those are your transcendental ones, in short. Okay. But anyway, we're not here to discuss all of that, but I just wanted to mention that is how it's normally done. Right. Okay. So now we finally get to Cantor's theorem, which we have proved. I think this will be all. I think this is the third time I've spoken about Cantor's theorem. I spoke about it on the very first day, and all that it says is that for any set A is of strictly lesser power than its power set. Okay. In other words, what this means is there is an injection from A to the power set, but no surjection. Okay. Can you give me an injection from A to the power set?
Identity?
The identity function. How? If I pick an element x in A, is x in the power set of A?
Well, since A has to be the collection of all possible subsets, since the power set of A has to contain all possible subsets of A,
Yes.
it also has to contain A itself because
Power set need not be what is the word? We had what was it? I want to say a transitive set. Why would it be transitive?
positive.
Transitive, meaning if A is an element of B, then A is a subset of B. So, I mean, let's just look at the set 2. What is the power set? Empty, 2. Neither 0 nor 1 is in there.
Yeah, but 2 is in there.
Yeah.
So
2 is in here, but 2 is not in here.
Yeah, but like
0 is in here, but 0 is not in here. You understand what I'm saying? What you can do is this. So I think that's what you wanted to do, but yeah, so just be a bit careful. You see, send x to the singleton, and that's of course an injector function. So this basically gives us that A is of lesser or equal power than the power set. Now to show that it's strictly smaller, we need to show that there's no bijection. Okay, so suppose we have any function g from A to the power set. Anyone, doesn't matter. Suppose g is surjective. Okay? What we do is if g is surjective, then I will look at a subset of A, which are all elements of A, for which x is not an element of gx. Okay, now recall g of x is a subset of A, so it does make sense to say x is an element of a subset of A or not, because x is also an element of A. So this is a subset of A. In other words, an element of the power set of A. Now, if g is surjective, then this must be equals to g of y for some y in my set A. And now we ask the fundamental question: is y an element of gy? Right. Now remember, gy is a set. If y is an element of gy, then what? Well, then y lies here. So if y is in there, then y is also not in gy. Right. And if y is not an element of gy, then it's still an element of A, and it must lie here. So from this, there's only one thing we can conclude, is that no such y can exist. Because if it does, we get a contradiction. Hence, G cannot be surjective. Okay, so this is Cantor's theorem, and this is what I call a brilliant proof. Because it's short and, well, sweet perhaps, I don't know. But it's a brilliant idea. Because it's a difficult statement to prove for infinite sets, I'd say. That there's no bijection. Sure, it's easy to prove that the one is of lesser than or equal power. That is trivial. But this part is genius, if you ask me. But I mean, we know that Georg Cantor was not a stupid person. Right. Probably because he wasn't doing physics. Okay, I'm just joking. Well, it is funny though. Right, okay, anyway, so let's talk about this. Okay, so this is basically what we have, and then we have some nice little corollaries here. If B is a subset of A, then B is not equipotent to the power set of A. Why? Well, suppose B is a subset of A, and B, of course, B being a subset of A implies what? In terms of B and A now. Okay, forget about the power set now first. Is B smaller than A? In other words, is B of lesser power than A? Or A of lesser power than B? Or neither?
B has to be of lesser
or equal power than A. Why? Because I can define the inclusion function by just sending B to itself. Now, of course, if B is equals to A, this is a bijection, but otherwise it's still an injection. So saying that B is a subset of A is also the same here as saying, well, it's not the same, but it implies that B is of lesser or equal power than A. So, remember, we don't really know anything about this ordering yet. And this is kind of the purpose of this section, is to develop some notions. So, if B were to be equipotent to the power set of A, then there's a bijection from the power set of A to B, or an F. And then, B, I have an injection that goes to A. So I have an injection from the power set to the set itself. Okay, is that possible? Do you think it's possible? It's probably not possible, right? I mean, okay, it isn't possible. Why is there no injection from a power set to the set itself? This is not entirely a trivial question. Well, if there's an injection, so forget about the name, but let's just call it H. By the way, sometimes you might see for one-to-one, people might do this for the arrows, for one-to-one, and then, or they might do this, but that is usually reserved for an inclusion function. or for a surjection, they might do that. And then if you want onto and one-to-one, you can do this, of course. Or some other people just do that for bijection. But that's also sometimes used for isomorphism explicitly. So if you ever do see these notations, that's more generally what they mean. So if I have an injection from the bound set to the set, first off, A can't be empty. Why? Well, because if A is empty, then the bound set is non-empty, and then I have a function from a non-empty set to an empty set, which is impossible. So if there is an injection from the bound set to the set, then that set must be non-empty. And now we have proven that if I have a function with non-empty domain, that was the important part, then that function is injective if and only if it has a left inverse. So if this function is injective, there exists a function g from A to the power set of A. And this function then satisfies this. Turns out, you can prove that H is injective and G is surjective. So then I have a surjection from A to the power set of A, which is not possible. Okay, right. So that is why there's no injection from a power set to the set itself. Okay, so of course, this F can't exist. Okay, because otherwise I have an injection from the power set to the set. The next one is A cannot be equipotent for all sets B for which the power set of A is a subset of B. We also have that A is not equipotent to B. Why is this? Well, it kind of makes sense. You want to think about, oh, A is smaller than the power set of A, and the power set of A is smaller than B, so you kind of want to think that A should be of lesser, strictly lesser power than B, right? So that would be the idea. So why is this the case? Well, if A and B are equipotent, then you have a bijection between B and A. Okay, and if you have a bijection between B and A, and I also have an injection from the power set of A to B. So I have an injection and a bijection, so I have an injection from the power set of A into A, which is not possible, once again. Okay, so in other words, our ideas at least about the sizes of set does seem to kind of work. Okay, and then the last one immediately from these two, if you have a subset of A, then B is of strictly lesser power than the power set of A. Okay, why is that? Well, of course, you can find an injection from B to A and one from A to the power set of A, so B is of less than or equal power to power set of A. Why is it, can't it be bijective? Well, we just showed that. Okay, so immediately from the first fact that follows, and then from the second one, wait, what's the second one? Did I write it down? Oh yeah. For all B that contains, yeah. So here they use D, so I'll stick with the same. If power set of A is contained in D, then we immediately have that A is of lesser power than D, strictly lesser. Simply because, once again, the second fact gives you, of course, there's an injection from A to the power set of A, and then one from the power set of A into D, so the composition is still 1 to 1. And then, of course, it's of lesser than or equal power, and it can't be equipotent because otherwise it would contradict that statement, okay, which we just argued is true. So these two things hold. So at least you have some comparison by using power sets. Okay. Now we have also, for finite sets, we have this chain of cardinal numbers. 0 is a subset of 1, subset of 2, etc. And this kind of gives us all finite sets in a certain way, up to defining some bijection. Okay? Now, for infinite sets, we can start with omega, or any infinite set if you like, okay? And now, this is of course of strictly lesser power than the power set. That's the power set axiom, so I can apply it again, which I will just write as that. And I can continue in this manner forever, counting them many times. Okay. Now what I can do is these are all sets by the power set axiom. So I can let my set, let's say T, be equals to the union of all these. By the way, you can replace omega by any set. Take the union of all of those. It's a countable union. It's a set. And now, this T is also larger in size than all of them. And then you can take the power set of T again. And you go, and you say, alright, we do this. And we continue in the same manner. Once again, you take the union and you can get something bigger. And we can do this as many times as we like. And so the thing is, there's a hierarchy of infinite sets, and there doesn't seem to be a largest one. Okay. Turns out what we will do later is we will, in some sense, we will get to argue that the number of different sizes of infinite sets is not just countable. It's probably larger than any of us can imagine. Okay. It's basically, you can think about the cardinality or the size of that as the same number of sets that exist. Okay. But I'm not going to talk about that directly now. But using Cantor's theorem, basically it gives us an infinite number of different infinite sizes of sets. Now, sometimes it's not really as commonly used anymore, but they used to denote it by the Greek letter, the smallest size of infinity. This is pronounced Aleph Null. Okay, it's a Hebrew letter, Aleph. And basically this was to say, okay, omega, you would say that a set is equipotent if basically it has cardinality Aleph Null. Okay. And one of the reasons why I think it's probably not used anymore, because you would say that cardinality directly after that is Aleph 1. But that kind of implies that there maybe might only be counts on many. So it's not really used because it's, well, say it like it is, it's a shitty notation. So we don't use this anymore. One particular question, we do know that this is the case. Now one question is, can I find any set A for which the cardinality is strictly larger than that here and strictly smaller than that there? Now, because for real numbers we just use decimal notation, we don't have to use decimal, we could use any other base we want, and particularly if you use base 2, then basically all your real numbers between 0 and 1 will look something like this, where each r sub I is equal to 0 or 1. And then you can quickly see that, by the way, also something, remember if I had a to the power b, we said it's all the functions from b to a. So 2 to the a is all the functions from the set a into 2. Okay? And the power set of a is denoted by that, and I have spoken earlier that you can find a bijection between these two. By here, if you have a function from a into 2, you send it to f of the singleton 1, if you like. It's a subset of a. Oh, sorry. No. 2 to the a, so you have a function from a into 2. Oh. Now I'm confused. Oh yeah, sorry. The preimage. Okay, so of course you take 1 and you look at everything that maps to 1, that will be a subset of A again. And on the other hand, if you have a subset of A, you just define a characteristic function of that subset. So everything that's in B goes to 1, and everything that's not in B goes to 0. And these two So basically B goes into that characteristic function, and these two functions between the two are actually inverses. Okay. So there's bijection between the power set of any set and all the functions from the set into the two elements set 2. So here, the power set, really you can view as all functions from omega into 2. It will have the same size. Now viewing the real numbers as just a function for every integer, you just choose the decimal, which is either 0 or 1. This has got the same cardinality as the real numbers. Okay, so the question becomes, is there any set that has size something between the natural numbers and the real numbers? And this is also known as the continuum hypothesis, and we don't know. This is an open problem. Don't know if you've ever heard about the continuum hypothesis. Okay? But it's not entirely open anymore. Let me rather say this. I think somebody has proven that it's actually independent from the rest of the axioms. In other words, it's undecidable. We can't say. And there's also a generalized continuum hypothesis by just changing omega to any infinite set x and asking the same. Is there a set A, which is cardinality between A and the power set of A? Okay. Which is just called the generalized continuum hypothesis, and these problems have not been solved. Okay. Right, so it's...
Now, just something struck me now. How is it that if we consider the natural numbers and like in decimal notation, they would like just be a sequence of numbers expanding to the left, like forever, but the real numbers is just a sequence of numbers expanding to the right forever?
What do you mean by the natural numbers being a sequence expanding to the left?
Like all possible natural numbers, that is just a sequence of numbers, like it will be 0 and 0 and 1, and then you have 100, or 0 and 1.
So are you talking about a sequence of natural numbers in particular, or all sequences of natural numbers?
No, the like writing the like any natural number is just a sequence of digits, right?
A natural number?
Yes.
Well, here it's just a set, 0 up to n minus 1.
Yeah, but like the same can be argued for the real numbers. Like it's also just...
Yeah, well, I mean, yes, but now, okay, so n I can of course just write like that. I don't need anything more, that's fine. I mean, of course I know that this is then, we define it as the set. Well, it turns out to be that, we didn't define it like that, we defined it recursively, or inductively. Okay, so we have that. But we can only use n, we don't have to, we can use our recursion theorem to know this, we can just list it as one thing. Even though it's all the cardinal numbers, I mean, the initial segment as a subset now of omega is just n. All the natural numbers smaller than n is just the initial segment of n here. But the real numbers, of course, here is, because of the way also, like I said, that's also why I mentioned, we can define it as equivalence classes of Cauchy sequences. When I mean the real number p, as an example, I really mean an equivalence class of a bunch of Cauchy sequences. Truth be told, is we only have to take one representative, because you can show that by adding the sequences like pairwise and multiplying the elements pairwise as well. It turns out, whether you do it for, of course you want to look at the equivalence class at the end of the sum, but you can take any representative of any of those two and it will still be well defined. In a similar manner, we would take two different representatives of the coset and you multiply them. It's not going to change the answer what the class or the coset will be again. So for real numbers, I'm not sure exactly if this is what you're heading towards, but for real numbers, of course, really this is an equivalence class of Cauchy sequences. But really, if I write down p, I can view it as the sequence 3.14, 3.141, and I mean there's infinitely many which will converge. So as long as these are all rational numbers, there's infinitely many that converge to it. But I only need to look at one representative at a time. So instead of a real number, you just view it as writing a bunch of digits down. You should actually more like think about it like a sequence, because that's formally, technically how it's defined. That's the one way, and the other way which you might have read about is called via Dedekind cuts.
Like Dedekind.
Yeah. Basically what you normally do is you look at the rational numbers and you look at all the numbers smaller than a particular one, and that's of course a subset. So you do them for larger and greater ones, and then basically that's of course, if you look at all of those subsets, then you eventually get a subset of the power set of Q, right? Of the rational numbers. And then you kind of define an operation there in some way. I'm not going to go into that in detail now, but that's also a way to construct a real number. So then you can also view every real number as a set, but already then they have this, they have the same size as the power set of Q itself, which comes back down to once again that argument. So that's the same cardinality already. It can't be the same cardinality as the original one. I don't know if that really answers your question, because
no, but I need to find a good way to formulate it and figure out why it doesn't work.
Okay, well, I'll think about it. If you can come up with because I'm not exactly sure what you mean. You say now this is a sequence, yes, but it's also just, we have to start on number n just by the recursion theorem, so we don't need anything else for it.
No, like you can write down like we wrote down the real numbers, like that as an infinite sum with 10 to the minus 1, where each SI is now a digit between 0 and 9.
Yes.
Well, why can't we do that also with the natural numbers, where like it's
okay, so this is every real number here between 0 and 1, of course.
Yeah.
Of course, now I can just make this S0. Now you just need to make this from 0. And then, of course, now here, S0, you just have to be a bit less restrictive by saying that could be any integer,
yes,
positive or negative, of course. And then, fine, you will get all real numbers, okay, like that. So for the binary ones, what I did is I only changed SI to 0 or 1, forget about S naught now, and I just make this 2 to the I. And you can still represent it. Of course, it's not an easy task to convert an irrational number into binary form. I mean, it's rational, it's not too hard. It's a bit weird, but it's not too hard. But irrational, I mean, you can try and convert pi into a binary number and get a few digits. It's quite tedious. It's not a nice task to do. So you can still just argue like, oh, it has some representation, just like it does for the decimal system, but finding it is not trivial. So we have already found it for base 10, so let's not do the others. All of them. It's going to take a while. If you want to do all of them anyway, I don't think you can. Well, you won't be able to get all of them anyway, but yeah. So I'm not exactly sure, but like I said, think about it. If you can get a nice way to ask it that I understand what you mean, I will try and answer you as best as I can. But I think, yeah, you can write the natural numbers like this, but then these are all just zeros afterwards, right?
Yeah.
So I guess in some sense, you just choose one element, because these are just 0. So these are, you can still view them as functions here from omega into 2, but you only define omega of 0, and the rest is just 0. So you would say that the natural numbers corresponds to all functions here, for which f, well, we do need to be careful for that though, but the idea is that f of n is 0 for every n. Of course, here, now I'm cheating a little bit because it's just the size that's the same, but the point here is if you go back to the power set part, then you can get it for all n greater than or equals to 1. So for the function, you only defined it one day. Maybe that is closer to what you're thinking about. Not sure, but I think it might be. Okay. Right. Okay, so we have this hierarchy of infinite sets and the continuum hypothesis. Okay, and now we also said that A is of lesser or equal power than B, and written like that if there's one-to-one function from A to B. Now notice when I said there's no injection from the power set into A, I used the fact that any function with a non-empty domain that's injective has a left inverse. So this is also equivalent to there is a surjective function from B to A. Okay, but why is it equivalent? Well, obviously, first let's do the easy case. Or maybe we should look at the hard case first. Well, no, let's do the easy case first. So if I have an injection from A to B, I know that there is a surjective function, G, that's the left inverse. So the composition here is the identity on the set A. Right? Okay? Provided that A is non-empty. Okay? Otherwise there's no function from B to A. So if A is non-empty, then you have the existence of such a G, and you can easily go and prove that this G will be onto. Because given any element A in A, f of A is an element for which G of f of A is equals to A. So G is surjective. So if A is non-empty and you have an injection from A to B, you have a surjection from B to A. So that part is clear. If you have a surjection, then by the way, by the axiom of choice, every surjective function has a right inverse, which is equivalent to the axiom of choice. It sneaks up on you again, but so use the axiom of choice here. But if you have a surjective function from B to A, it has a right inverse, call it f, and then that f will be injective, as you can go and prove. Okay, because if f of A is equals to f of A prime, then g f A must be equals to g f A prime, and g f is just identity, so is A prime. So the left inverse will always be surjective, and the right one will always be injective. So if you have G composed of f as the identity, 1 to 1, 1 to, always. So if we have the surjective function from B to A, then of course we have an injection function from A to B. But okay, now there's one thing I skipped. What if A is empty for the forward direction of the proof? Well, then no, it doesn't quite work out now, does it? Okay, so this is probably, just want to check, it's probably not going to help if I give you the page number, right? Well, where was it though? Yeah, okay, it's 0.7.7, it's under section 7.2. So this is a mistake in the book as well. That statement is only true if A is non-empty. Okay, because if A is empty, then of course there's an injective function from A into A respectively. Okay, however, if B is non-empty, there's no function from B to empty. Okay, so the reverse direction still works, but the forward direction does not. Another mistake in the book. It's number 2 now. And notice that this is only a mistake because of the first mistake. That says that there's an injection from A to B if and only if it has a left inverse. Because that was wrong. Because A had to be non-empty there. So the mistake is just carried over here. Okay? Hence, A must be non-empty for this to be entirely true. But most of the time, it's anyway quite stupid to think about A being have lesser power than B if A is empty. Of course it is. So if you forget about that case, For all non-empty sets, that is still true, which is anyway, I think, more the purpose of the idea. So even though it's a mistake, it's not a big one. It's still a mistake nonetheless, but it's not really going to influence the theory. Okay, as long as you just keep in mind that, oh, okay, well, the empty set is a trivial case. Right, please notice that if you have a surjective function to the empty set, then B must also be empty. So then they're actually equipotent. Like I said, so the reverse direction is anyway still true, but the forward implication is not. Okay, so that's something to keep in mind. Okay, right. Okay, so I wanted to say that. Right, so now we have a few other things here. If you have, so we're just going to be also comparing some of the sizes of sets by using functions. So if you have that A and C are sets, and the intersection of A and C is empty, and also the intersection of B and D are also empty. Okay, so A, B, C, and D are sets. A is a function from, or F is a function from A to B, and I have G is a function from C to D. Now, of course, if they are both bijections, then I can still view F, I can enlarge the codomain of both F and G as a function from A to B union D, and similarly here G from C to B union D. Right. And these are not bijections anymore, they're injective. The new ones here. So I'm giving them the same name, but they're not really the same. Now, of course, as sets, these are still subsets. This one is a subset of A cross B union D, and this one is a subset of C cross B union D. So if I take a union of them, it will be a subset of A cross C, A union C, sorry, cross B union D. So it is then a relation and it's quite an easy exercise to go and prove that this new relation is still a function and it is actually still a bijection. And of course you need the fact that A and C are pairwise disjoint, otherwise it would not be a function, because you might F and G have going the same element going to do different things, of course, because B and D are I mean, there's no, and of course for the onto-ness and for the one-to-one-ness, you're going to have to use these things, but it's pretty easy exercise. Anyway, I think the proof is there. I'm not going to go through it. But here, anyway, with the proof, what they do here, you can't prove it directly, but what they do is they actually use the inverse relations, and what they do is they show that F inverse union G inverse as relations. If I take the composition with this one, then I just get the identity in both directions. So that's kind of like what they do. Okay, so basically now, and one thing that follows from here is if A is equipotent to B, and this is kind of why we do this idea, if A is equipotent to B, and C is equipotent to D, in other words we have such bijections, F and G, then of course I can now say A union B is equipotent to C union D. Which is something, I guess, which is nice to have, right? Okay? So that's something that follows from here. Another thing, so still we have such bijections. I'm just going to see what is the next one. Okay, so there's actually a few. Let me write all of them down. Then we don't need to worry. So once again, I assume that's the case. So if A and B are equipotent, then well, one that holds. Another one is B to the A will be equipotent to not B to the A. Let's say C to the A will be equipotent to D to the B. Now, of course, here by this I mean all functions from A to C and B to D. And then also A cross C will be equipotent to B cross D as Cartesian products. And what else is there? That's about it. Oh, and then the last one, A, power set of A is equipotent to the power set of B. Okay, so we've seen the first one, follows from there. The second one, if you have a function where you want to define a bijection from there to there, I will still assume f and g are the bijections as above, f from A to B and g from B to C. Now think about it, if we call this, let's call this h, capital H, just to give you an idea. You want to take a function f from A to C, and what you want to get is something that's a function from B to D. Okay, we want to know how to define that. So you think I have a function from A to C. Okay, call it f. No, let's not call it f. Let's call this k. I am given a function from A to B, which is a bijection. I'm given a bijection from C to D. So how can I use a function from A to C to get one from B to D? Okay, so you just define h of k to be gk f inverse. And you can easily show that this is a bijection between all the functions from A to C and B to D. To see that it's injective, if hk1 is equals to hk2, then gk1 f inverse will be equals to gk2 f inverse. And then of course, you could just use injectivity and the fact that these functions have inverses, just like you would for groups, to show that k1 is k2. And then also for the surjectivity, if you want a specific, let's say L from B to D, then you only want L to be equals to gk f inverse for some k. To find that k, it's like a group operation, multiply by g inverse on the left and f on the right. And so you just let k equals to g inverse LF. And it will work, right? So those are the same, A cross C to B cross D. You define a function which I will just denote like f cross g, where f cross g applied on a pair form AC, I just define as the pair f of A, g of C, and that will give you a bijection. So the Cartesian products are also then equipotent. Okay, and for the power set, that's also easy. If you have f being the bijection between, I will just call denote like this, because I'm used to the notation, but I define function from here to here. If f was a bijection, and this on a particular set A, no, not A, so a subset of A, say X, is just defined as the image. And you don't show that that's a bijection. Right. So a lot of properties by taking power sets, Cartesian products, and functions from set to set works in the same way. In particular, another one that's quite useful is we have A and B equipotent and C and D equipotent. Then I might also say, let's say C is a subset of A and D is a subset of B. Okay, now how about if we compare A without C and D without B? Where A and B are equipotent and D and C are equipotent, would you expect this to be the case? Or would you like that to be the case? In other words, if A has the same size as D, oh no, sorry. Sorry about that, otherwise it would be really a bit weird. If you told me you'd like that to be the case, maybe that would have been an odd answer. But okay, so A and B has the same size and C and D has the same size. You kind of expect these two to also have the same size. So this one's a bit trickier. Why would that be the case? Okay, so we have bijections from A to B, and we also have a bijection from C to D. So how am I going to define a bijection from A without C to B without D? Any ideas? I wonder if this one's even in the book. Should be in there. Oh, it's one of your exercises. Perhaps you should just leave it as one of your exercises because it's a good exercise. It's not entirely trivial. The reason why it's not entirely trivial is because you would like all the elements of A that are not in C to map to all the elements in B that are not in D. But truth be told, there's no reason for that to be the case, generally speaking, so why then are they still bijective? So I might give you a little bit of a tip. Think about the set A as A without C, union C. Think about the way we took the unions of two functions over there. Okay, by the way, also maybe another thing I should mention. Everywhere here we assume that A and B and C and D, or A and C and B and D were disjoint. That's not really an issue because if you have two sets that have an element in common, let's say A and B have an element in common, if I want to make them disjoint, I have an equipotent set that's equipotent to A by simply sending A naught to A, or A to A naught on the other hand, and so you can make even the same set. They are both equipotent to itself, but even these are disjoint. Okay. So if you have two sets with an element in common, you can always make them disjoint. And that's of course true for any, if you have any family of sets. Okay. Even class indexed, you can still make them disjoint in this regard. Okay. Right. So go and prove that as an exercise. I think it is a good one to prove. Like I said, think about this union part as a little bit of a hint. Okay. Right. And same, by the way, it's also an exercise. Same is true for unions and products as well, or arbitrary products. So just use the ideas here and extend them to infinite cases. Okay. Right. Now we'll look a bit about infinite sets now, because we've discussed a lot about finite sets, and now we have a little bit of an idea, at least a bit more, how this so-called cardinality argument we haven't defined, but how we want it to kind of work, we have an idea. Because what we really want is we want a family of sets that are well ordered, that will come later, but in particular every set we want to be equipotent to one such cardinal number, and not only that, we want that number to be unique. In other words, for every set has a unique cardinal number for which it's equipotent to. Okay. So that's kind of what we want out of this, and this is just some tools to develop that for later, or to develop some of the notions that we will use there, also to add and multiply these numbers. Let me just check we're okay that I was talking about. Okay, so now we've got one definition of infinity or infinite set. A is infinite if it's not finite. That's our definition, but we've also got another one. A is infinite if it has a denumerable subset. Okay, of course we need to prove that this is the case first, but this will be an equivalent definition. And also there's another definition. A is infinite if and only if there exists a proper subset B of A for which B is equipotent to A. Okay, so for example, what you can think about A there being infinite, of course, like if you take the natural numbers, or if you take the integers, then of course it's just equipotent to the even integers by just sending n to 2a. Okay, so of course we know of examples of this. But you can also take this as a definition. Of course, we first need to see that these two things are actually equivalent definitions. Okay? So I'm just stating them for now. We'll prove everything about it now. So the first thing I want to do is okay, so let me just see where I'm going to start again. Okay. First off, what we prove is we prove the first statement for the enumerable subsets. Okay? So, well, not exactly the first statement, but we prove the second statement for the enumerable subsets. Okay, not exactly that either. Okay, well, we started with a lemma. Anyway, there's quite a few things here. So, lemma is if A is denumerable, okay, and X is an element of A, then A without X is still denumerable. So in other words, by removing one member, it's still then of course denumerable. The same will apply to adding one member, and because you can do this finitely many times, countable union finite or countable without finite remains countable. Okay. Or denumerable in this case, which is more important. Okay. So let's see why. If A is denumerable, then we have a bijection from omega to A. Now, what did I want to say? Okay, so we have the bijection from omega to A. And now the point is also, so think about it like here's omega, and here's A, and that's 0, this is, of course, f of 0, and this is 1, and this is, of course, f of 1, and so forth. So that's your function f, goes in that direction. And now for this particular x, it lies in A, so f of n is equals to x for some n. So at some point here, you will get to n, and then here what you will have is f of n minus 1, here you have f of n, and here you have f of n plus 1. Now of course the f of n is x. So now I remove this x. So what I do is, now remember the function f, you just go like that if you want to define it. So what I do is, I define g of n is equals to, well, for the first n minus 1 ones, I just define it to be the same as f. Okay? So f of n, if n is smaller than n. Okay? And now, what do I want? I don't want g of n, I don't want to be x, because I don't want x to be in there. So all I do is, I just send it one down, and I continue in that manner. So I define g of n to be fn plus 1 if n is greater or equals to n. And I think from the picture, it should be clear that it will still be a bijection. You can prove it, I'm not going to. I think it's relatively easy to see, okay, by just using the fact that f is a bijection. Okay, so if by removing one point still makes it denumerable, it's not going to change the signs. Okay, next, right. So if by removing or adding a finite set to a denumerable set doesn't change the fact that it's still denumerable. Next thing is if A is infinite, then it has A is infinite. So that's the next thing we prove. That's statement 1. If and only if it has a denumerable subset. Okay. So I will just call it statement 1, or I. So let's prove this. The forward implication. Okay. If I have an infinite set, okay, now I only know that it's not finite. However, omega is an infinite set, and in particular, omega is a well-ordered set. Right. Now we can of course well order our set as well. So if our second question is A, we can well order A. Okay? So I well order my set A. So here, of course, keep in mind, axiom of choice. Well ordered my set A, and what I now know is that omega is also a well ordered set. And now remember, for well ordered sets, we can compare the sizes. So we have the result that says one of the following things, exactly one of the following three things need to be true. Either omega is equipotent to the set A, okay, or omega is isomorphic or equipotent to an initial segment of A, or A is equipotent to an initial segment of the natural numbers. Exactly one of those three things need to hold. Okay. Now in case number 1 holds, well then A itself is the denumerable subset of A. Because A is then denumerable. Because it's equipotent. So in case 1, we've got nothing to do. Now, in case 2, omega is isomorphic or equipotent here to an initial segment of A. So there's a bijection between omega and the initial segment of A. So this is a denumerable subset of A itself because it's equipotent to omega. So we're done. What happens in case 3? Now A is, if this is the case, I mean we don't know. Well, the point is to show that this can't be the case. Okay? Now, the initial segment, remember the initial segment of any set, if you have an ordered set A, or let's say X here, then the initial segment S sub X is all elements that are strictly smaller than X. So Sn here is just the natural number A. Okay? So if A is equipotent to N, well then A is finite. And that's not possible because we had by definition or by assumption A was infinite. So this case can't happen. So either way, A has a denumerable subset. Okay, so this is like the sketches to prove. Okay, the reverse implication, suppose A has a denumerable subset. And now we need to prove that A is infinite. Okay, so what we do here, it's an induction argument, right? So what we prove is that, so we assume that A is denumerable, and we prove that for every n greater or equals to 0 now here, n is not equipotent to A. Because if we can do this for every natural number, then A must be infinite. Okay, so we use proof by induction on n, that this is the case. So for n equals 0, I think it's of course trivial. Okay, because of course A, remember I assume now that A has a denumerable subset. And now if A is equipotent to 0, namely the empty set, then of course it can't have a denumerable subset because it only has one subset, namely the empty set which is empty, which is not denumerable. So for n equals 0, the statement is pretty obvious. Now, let's assume that it is the case that A is not equipotent for all natural numbers up to some n. Okay, so we go basically use strong induction. And now we consider, we want to prove that this is not equipotent to n plus, the successor. Now, A has a denumerable subset, call it S. Okay? Now, if n is not an element of S, right, then S is a denumerable subset of n. Okay, remember here, well, maybe I shouldn't say, well, I want to say like the image of a denumerable subset. I mean, okay, maybe I should rephrase this a bit better. because that statement right there doesn't make sense at the moment. In my head, I know what I mean, but what I'm writing down is wrong. Okay, so let me just go check. Where am I going? Okay, well, basically what we do here is we just show that every natural number does not have a denumerable subset first. Okay, so you'll get to my induction, but we do that by induction. So of course for empty, and then we assume it's the case. Now, if n has a denumerable subset S, n plus has a denumerable subset S, now we assume that for all k from 0 up to n does not have a denumerable subset. So if n is not in S, then of course S is a subset of n, and then n has a denumerable subset, which is a contradiction because n doesn't have by induction hypothesis. Now if n is an element of S, now remember S is a denumerable subset of n, so forget about A here. So n is a subset of S, and so now we know that S without n is still denumerable, because we can remove any finite set, and this is a subset of n, so then this is a denumerable subset of n, so it's a contradiction. So in other words, for all by induction, then for all natural numbers n, it has no denumerable subset, which in particular implies every finite, or every subset of a finite set is finite, which is something which we actually then kind of proved indirectly here. So it's also a corollary of this result by just using the idea in the proof. So it's not something we assume, it's something that follows from our ordering here. And now the point is just that if A has a denumerable subset, then it can't be finite. Because if it is finite, then it's equipotent to some n, and A being equipotent to n via some function, let's say f from a to n, and you have a denumerable subset S of A, and if f is a function from a to n, then you could say f of S as the subset of n must now also be denumerable, okay, because f is 1 to 1. By the way, if you have a 1 to 1 function, the size is always the same as the image, because you can restrict the codomain to the image and then you have a bijection. So because of that, if you had A being finite, then it would imply that you have a denumerable subset of a natural number, which is not possible. So that's why the proof follows. Okay, so sorry for my error there. But so for all n, n has no, let's say, equipotence. Well, n is finite in the first place, but so that's also wrong. It has no denumerable subset of all natural numbers. So that implies that every finite subset, every subset of a finite set is finite. Sorry. Right. In particular, another thing it implies is if you have an infinite subset of a set, then that set must be infinite, the larger set. And then if you have an infinite set and you have a non-empty set, let's say A is infinite and B is non-empty, then the Cartesian product A cross B and B cross A are both infinite. Why? Because A cross singleton B or B cross singleton A are both infinite subsets of A cross B and B cross A respectively. Okay, so that also follows. You can do it via a function, but anyway, that's the idea. And now our other theorem just says, and that's the second one there, statement 2. What's the time, by the way? I feel like we are, okay, my timing is pretty good. I was about to say, I think we're probably getting to the end. Although don't worry, I've already prepared enough lectures so we can continue until 4. I don't want to, but we can, theoretically. Okay, so what was I saying? This is also why we shouldn't continue to 4.
Exactly.
Because I have been also lecturing for an hour this morning right before I got here. So A is infinite if and only if there exists a proper subset B of A such that A and B are equipotent. Okay. Now A is infinite. Okay, then I can at least say, okay, fine. I can still well order A. And now one of three things must hold. Either omega, similar to here, omega is equipotent to A, right? In which case it's trivial, because I can just look at any subset here which has the same property, like the even positive or non-negative integers, and just use the bijection between them to translate it to construct a denumerable or an proper infinite denumerable, of course, subset of A. So that works. If omega is, so the first case also works, if omega is equipotent to an initial segment of A, well, then using the function from omega to the initial segment, of course, already gives me, well, okay, I'll get to that case now because that's the important one. Of course, A can't be here equipotent to Sn like that, because then A would be finite. Okay, we assume that A is infinite. Okay, so the only case that we really need to think about a bit is this one over here. Okay, now if we look at this particular case, this means I have a function f from omega to A. Okay, and what I do is, by the way, actually I don't even need to well order A now, but I think, well, anyway, doesn't really matter. We have already used the well ordering theorem, so it's not really going to make a difference now. So we have this function, and all we do is, this is really just a sequence. In fact, actually, I don't need to use the well ordering theorem. Screw it. Let's not use it. It's not necessary. We don't have to use it again. Technically, still relies on the results. It doesn't really matter. But okay, what I can do is A is infinite, so A has an enumerable subset. We proved that already. Right. So we can just view that as a sequence, etc. And now what I do is I define a function from A to A without A naught, and this function will be a bijection, and I define f of x as x if x is not equals to A sub n for every natural number n. Okay, so you fix the elements that are not in the sequence, and you define it as A sub k plus 1 if x is equals to ak for some k. Of course, that k here will be unique because we take the sequence of distinct elements here, because it's a subset. It's an enumerable subset, so in other words, and then this f becomes a bijection, and this is the b. It's a proper subset. So actually, I'm just really removing one element. Okay. But I just use the sequence or the enumerable subset to create a bijection out of it. Okay. So a set is infinite if and only if. Okay, well, so that proves a set is infinite if there's a proper subset that's equipotent to it. We also do need to look at the converse. Okay, if you do have a set, subset, proper subset of a set that's equipotent to it, why is it infinite? Well, suppose not. Then, if you have a proper subset, B of the set A, and A is not infinite, that implies A is finite, which implies B is finite. And now, if A contains n elements, this, whatever that is, n, must be strictly less than n, okay, because it's a proper subset. And now you can just use the fact that, okay, well, if this is the case, then of course, n minus n, I mean, you can't find, the point is that this is an n and that is n, and n must be strictly smaller than here, because it's a proper subset. Is that possible? Because if there's a bijection between a and b, let's say g, how many elements are in b in terms of the elements in a? If g is a bijection, then it must be n. because it's injective in particular. So in other words, because it's injective, G of A, the number of elements here must be n. N. The same as an A. So the point is A is equipotent to G of A because G is injective. Now because G is surjective here, this is just B. Okay, so then B must also contain it. Hence, A is infinite. Because if A is finite, we get a contradiction. Okay, I think, right. They use the recursion theorem here to prove it. But basically, they just pick an arbitrary element of A without B. And then by the recursion theorem, you have a function from the natural numbers to the set A for which gamma of naught is the C, the element they picked. And then gamma of the successor of n is f of gamma n. And then because the range of f is b, we had the previous result last week. We said, okay, well, if the f is injective, and then the gamma you get will also be injective, provided that the element is not in range. Now, because the c is not in the range of the function here, it will also be injective, so that's another way of showing it's infinite. But you can also go via contradiction with the finite points. Okay. Okay, let's do the last one, then I'll leave the next one for the next time, because that's quite I don't think I'll be able to finish that proof in 5 minutes. So just the last thing, every subset of a denumerable set, so for all x subset of A is equipotent. In other words, if A is denumerable, then x is finite or denumerable. Okay? Right. So if we have a set A and it's denumerable and I pick a subset of it, okay? Then of course, x, I have an injection from x to A. Okay, and then I also have a bijection from A to omega. So clearly there's an injection from x to omega. Okay? So it's technically already, but now, okay, so the point is if there is a bijection, then it's of course. So if there's a bijection from x to A, which could also only happen if A is infinite, or unless x is A, of course, then of course you know that x is then equipotent to omega. Now the only other thing is that, because now I just write x as, the power of x is less than or equal to omega, but the point is that this also means it's equipotent to omega or finite. So that I probably didn't state well here, but the point is this actually means that. Okay, but that's technically what we need to prove here as well. So why is it otherwise finite? Well, can it be the case that it's not denumerable and not finite? Well, if it's not denumerable, and you have a subset here, in other words, if x is not denumerable, and x is not finite, that means x is infinite and it's not equipotent to omega, right? So then omega would obviously, once again, you can well order it, but the point is omega will have to be strictly smaller than x then, because it's the smallest infinity size. Okay. But anyway, you can, the point here is that you actually need to realize that every subset of omega is either finite or denumerable. Obviously, if you take a subset of omega, if it has a maximum, it's finite. If it doesn't have a maximum, it is denumerable. Okay? So that's the first thing to realize, and then the point is the size of x will be the same as the injection applied on x, the composition of these two injections, which is then a subset of omega. So x is equipotent to a subset of omega, hence it must be finite or denumerable. Okay, that's kind of the point here. I'm not going to do the next theorem now, it will take too much time. However, basically what the theorem does, I'll give you a little bit of a proof sketch and then we'll formally prove it next time. So what the theorem says is omega is enumerable to the Cartesian product of it with itself. And basically, we will use the recursion theorem there, but basically if you try to sketch omega cross omega, just to give you the main idea. Right. Now what you do here is we're not entirely going to define a bijection, but what we will do here is we will send an element here, okay, so they denote it as pairs kn, okay, if the n is non-zero, in other words it's not here, okay, then you basically just map it down there, okay, so in other words, if m is not zero, then this gets assigned to k plus 1, m minus 1. No, sorry, it must go up. No, it must go down. Yeah, like that. The x coordinate moves 1 to the right, and y coordinate there. So also, you can see that that should happen. So in other words, even here, and so forth. Okay, and if n is 0, we send this element to that one there, because that's right where you can see the only elements that are not in the range are these. So you send that one here, the next one you send there, and here if this is k, k0, then that gets sent to k plus 1, or 0 k plus 1, sorry. Okay. So that's the function we'll be using, and then we'll prove a few things about this function.
Shouldn't it get sent to 0k?
No, because we don't want 0, 0 to be in the range. Basically what we're going to be doing is we're going to prove a few properties. The point is, I think from the picture it's not too hard anyway to see that this function is a bijection between omega cross omega without the point 0, 0 and omega cross omega. Okay, because given any point, okay, of course I think it's clear that it's 1 to 1. Okay, from omega cross omega to omega cross omega without the 0, 0. And then given, I think the 1 to 1 is clear, and the answer is, well, if the x coordinate is 0, k, then you just go and look for k minus 1, 0. And if the x coordinate is not 0, then you just, basically you subtract 1 from the x and add 1 to the n, so to speak. So this then becomes a bijection if you remove this, but now it's just a function from omega cross omega to omega cross omega, and then we had the same thing with we have this function, and now by recursion theorem, I choose a c that's not in the range of f, that one, and then I have the existence of a gamma, and that gamma will basically, it will give us the bijection, because gamma is then a function from the natural numbers, or from omega, into the set of ours, which is omega cross omega. And it turns out, well, we'll have to prove that that function is in fact bijective, which is not as clear, but basically that's the idea behind the proof. Okay, I'll continue with that next time. Any questions? Okay, Wednesday will be quite interesting, I hope. Then we'll do cardinal numbers, and I'll show you how you can multiply infinite numbers with each other. Right, also, I'm guessing these won't be here, so I don't have another memory stick. I think I borrowed out too many.
I found a few.
Okay, but anyway, like, yeah, so it would at least be nice if you could just bring that on Wednesday.